Hi and welcome back to the lab. Today I have here a handheld mobile radio. So that is a Kenwood TH-D72, and the D72 does not have output power on both 2 meter and 70 centimeters. So let's try and let's see how we can help. Okay, so here is our TH-D72, and yeah, let me first check what is going on. Okay, so it is switching in. Okay, it is on 340. Let me check here the band. Okay. Let's first check on 430, so 70 centimeters. And as you may see, we have it on high, which means we should get, let me say, 5 watt or something here out of our radio. Let me check if I can switch it. Yes, I can switch it over to transmit, and you see here the bars are coming up, so that is promising. Okay, so let's see what we see on our generator. Okay, so then let's see what we find. So we are on 430.050 and we have set the radio to high, and now let's press PTT. And yes, it is coming up on 430, approximately 50. But the battery is more or less empty. Okay, so let me connect the radio to the power supply. Okay, so radio is now connected to the power supply. And okay, let me press once again PTT. And yes, we see 0.7 of a watt on high, which is definitely too low, so we should be able to get approximately 5 watt. Okay, so let me switch over to 2 meter and let me use the frequency we see. Let's check if okay, yeah, so the radio is receiving, that is what we can hear. Okay, so, but that is not what we are looking for. Again, our transmitter is switched to high. And now let me check what we get out. And yeah, it is 0.7 of a watt once again. And that is definitely not what we would expect. So therefore, something is wrong, of course. Okay, but before we go in the radio, we should first perform a total reset. Sometimes it happens to be that if a setting is wrong, that the radio will not transmit as expected. So therefore, let's go into the menu and let's see where we find the needed setup. Oh, auxiliary reset, that looks good. Oh, that was obviously wrong, so we need to go into auxiliary. Where is it? There is reset. Okay, and we want a full reset. Let's see. Okay, full reset, sure. I mean, yes, that will delete everything what has been stored here, but we need to do that. Resetting. Oh, that takes a while, and it's coming back. Okay, so that is quite nice. and then let's see what we get. Let's go over to the tester. Okay, and that is of course now fresh resetted. So we are on 430. Let's test on high. Nope, that was not the problem, obviously. Let's go back to 2 meter, and even on 2 meter we only have not already 1 watt output on high. So what is when I go to low? That is now on low, and it is 0.1 of a watt. So that definitely means we have here a serious issue which is not software related. So yes, we have to go in, we need to crack open the radio. Okay, then we're going to start to take it apart, and okay, so you see our electric screwdriver is doing the job here without any problems. Even here, no problem. Very nice. Okay, so let's say, yeah, let me go ahead, and then we will come back when we are closer. Okay, first you need to remove here the speaker mic jack cover, and if that is removed, and here our knobs, we should be able to get here our unit out. Let's see. Yes, we can do it. Very nice. And now, as you can see, we can go ahead. Okay, so we have our radio so far taken apart, and you see now I can flip over here the board in order to get to our final stage, which is the chip here right in the middle. So this here is our final stage. The problem right now is we cannot really test the radio how we have it here. So therefore I need to prepare it here a little bit in order to be able to test it. Okay, so having said that, now everything is prepared. So we have seen here this little ribbon wire which normally connects over to the digital board, which we cannot do here in our test configuration. So therefore you may see that I have soldered here a little wire to the connector in order to be able to bring our unit into transmit. And you may already hear the tone here in the background. So the radio's already running, and now when I bring here our lead to ground like so, my radio is switching over to transmit, right? And so I'm able to test here at our power amplifier here down there, and yeah, everything is prepared. But let me show you once again how the output power is. So I've set here the radio to low, which means our radio should minimum produce 0.5 of a watt. And well, let me bring it into transmit, and let's see what we see on our service monitor. Alright, so now let me bring the radio into transmit, which we have now, and you see that we have 0.18 watt. So even here we have missing output power, so nothing changed. Now we can do our first test to see what's really going on here. Okay, so let's try to understand a little bit more when we go now into the testing. So we see here we have our final stage, and here our driver stage. So of course what we need to know is if both transistors are working, and of course if for instance this transistor is working in the right way, so everything in front of it is working as well. Then additional to that, we need to know first if our supply voltages are present. So for our final it is no problem, because we can test here for in receive 10.6 volt, and well, on transmit it is going down a little bit to 7.3, so that is very much important. And then what is important as well, so you may see that here in our signal path we have, so here that is our driver, that is a final, and you see when we go over our VHF way or path, you see we have here an RF switch, and that is nothing more than a diode. And of course a diode needs to get biased, and therefore we can see here that voltage, and a DC voltage, is going here to our diode, and then over here our 261 to ground. So that means that this diode is engaged, if you like. And when we go over here, so that is our DC voltage line for and you can see it here. So that is a DC switch. This is for 2 meter, so we can see it should be 3.7 volt. Receive of course 0 volt, and well, we need this switching voltage when the radio goes into transmit to switch on, if you like, this diodes here, the RF switch, and we have another RF switch behind our RF or final amp. So we have here 2 RF switches which gets switched in by the same DC voltage. So you see here, that is what we have already spoken about, and here we have our second pass where the both diodes gets engaged when we go into transmit. If that doesn't work, so then that could be reason for attenuating our output power. So that is very important to know. So our both switching voltages are absolutely essential, so we need to check that out. And besides that, of course, we need to check for bias voltage at our gate, so that is important as well. And then we need to go over to our level diagram, and we can see here in our level diagram the both transistors, and we see when we pick our signal at 260, we should find on VHF plus 9.5 dBm, and if 9.5 dBm are present at this point, then we should see at our antenna socket 0.5, so half of a watt. What we don't, right? So the radio is set to low, so that is the test requirement, and therefore we see here our 0.5 of a watt, and that is not, or that get not produced. So we have seen we have only 0.8 something of a watt, and that means something is wrong. So what we do now is we check all the voltages, the DC voltages we have discussed, and then we pick here our signal at C260 in order to see if our driver stage is working, and as already said, if that is working, everything in front of our driver is fine. So if that is present and if all voltages are there, we have to concentrate on all what is in between here. So that is the plan. Let's go into the testing. Alright, so the very first what we can test is at the power amplifier on drain. Let's see what we got. 7.57, so that is exactly what we find in our manual. And of course now we can set our unit into transmit, and here we have it. Very nice. And when I go now to the drain, we should see our level reduced. Let's see what we have, 7.57, so exactly what it should be. Okay, the next what we do is we check at our preamplifier, and I have already put here a little wire to our C260 so that we can grab here the level at the output, if you like, of our preamplifier, right? So that is the next what we do, and if we if we can find our required 9.5 dBm, then we know that the level and thus our driver stage is working, and then we need to go into the switching once again, where we need to know if our diodes are working. Okay, so you already see here the print, or not the print, the screen of our spectrum analyzer. So let me bring our unit into transmit, which we have and you already can see a signal, and I'm not finally here connected to the pin. So let me go down there. Very nice. 10.79, very nice. So required is 9.5 dBm according to our level diagram, and you see that is completely there, and that is very promising. So again, I was testing here at our C260, and we have above 10 dBm here at that point, and that means that our pre-driver, or not pre-driver, or our driver is delivering exactly what we expect, and that means that everything in front of it is working perfect. And again, what we see here, that is the point where we picked the signal and we were above 9.5 dBm, so which is absolutely fine. Well, and the question is, why don't we get out our expected half of a watt? So that is not clear, as already discussed. So it might be a problem with our final stage here, or it is something wrong with the switching, and that is what we need to find now. Okay, so let's watch out here for our Q208, which is delivering here our RF switching voltage. So we should see 3.7 volt if we go into transmit. So therefore, that is now exactly our next step. Alright, so let's exactly check that chip. And first, without going into transmit, we check the input of that little IC, and we should have, what was it, approximately 4.5 volt. So let's see, here it is. So that is perfect, 4.5 volt. And of course we need to switch our unit into transmit, what we do, of course. Okay, so now it is on transmit, and now we should see an output voltage on pin 6. So let me check through here, and I don't see nothing. What is the problem? I don't know. Let me check what we have. Is it... where is it? Come on, come on. Ah, here we are. 3.6 volt. So that is exactly our output voltage, and once again our input is 4.5 exactly, and output is 3.6, and that exactly is what we needed. Okay, so we really need now to conclude a little bit how to go ahead. I mean, here is the whole portion of the circuit which is important to us. So we know that the output power is reduced, and we do not really have at least found a fault where we clearly know that it is a problem. So let us summarize a little bit what we did. So first of all, we have here our power amplifier, so we have here our driver, and we have here our switching voltages, so where we get at least here the DC, and that is the DC for at least our pin diodes, which are here in the signal path. Very, very important to check that. And additionally, of course, we get here our main power supplied to our power amplifier, our pre-driver, and some other stages that they have their normal voltages to work. So then there is another part which we have, and that is our APC, our automatic power control. And all of these different portions of the stage here could have an impact on what we see, or the fault picture we see. And therefore we really went through the circuit, and we tested the different voltages and the different conditions. And the last what we have done, so let me enlarge it a little bit. So we were working here on our Q208, and we tested the input and the output, and that all is fine. When we go over and we look what this voltage is supplying, so once again that we all remember, so this is bias voltage for our pin diodes. So that is very important, because without this bias voltage, simply our power amplifier wouldn't amplify the signal. And of course that could be a reason. If something is wrong, either the voltage is itself or one of our diodes, which are here, for instance, as well in our signal path, so everything could have part of the problem. And then of course, beside the fact that we do not know yet if we have a problem here with our final, we know that our pre-driver is obviously good, because we have tested it with 10 something dBm, so that is above the level we have seen in our specs or in our level plan from what we get delivered with our service manual. And of course then we have the APC, or the ALC, automatic level control, or automatic power control, and that is here our APC circuit. And that of course is very important as well. So we get from here our supply voltage, and you see our supply voltage gets over this both resistors and goes up to when we follow this line. So we see that is plus B, which is supplying our pre-driver as well as our power amplifier, which we have down here. So that all gets controlled by our APC controller, which is sitting here. And since the voltage, and that means as well the current, goes over this both resistors here, which are switched in parallel, and of course you will have finally a voltage drop here at our resistors, depending on the current which is flowing through this resistors. And that means depending on the current you have a different voltage drop, and that means of course that if that will then get controlled by our APC, then you can compare the input or the current which you expect and the current which might be too high. So therefore you can give here at the output an indication of what your current is running through our final and pre-final. And therefore we have here a voltage which depends finally on what is happening here at our measuring resistors, if we want to call it that way. And then you see that this voltage is simply going here to the negative input of our operational amplifier, our IC203, and on the other hand, and that is a positive input, you can see it is coming here over our D209, and you can see here APC. And that is again what we have heard so often, that we get here our selection from our microprocessor, our MCU, where you tell the radio low, high or EL, which is once again a reduced output power. So you have 3 different levels which gets predefined over your MCU, and you get here then the respective voltage, which is going here to our input, to our, once again, to our positive input. And that means if you have here a positive input, then you get here a positive output, which is then supplying, and you can see it here, our BIOS voltages. So once it is here for our driver, and of course it is the same here for our final. So that is exactly the same. And of course, as long we have here a positive voltage, depending on the power you want the radio to send out, you have a positive voltage. But this positive voltage, which then leads to our bias voltage at the gates of our transistors, gets interrupted, if you like, when this level here gets too high at our negative input. So then this comparator, what it is comparing the 2 voltage, so the reference voltage from our MCU and the real voltage, what we get here over our resistors. So that is then the real feedback, what the current is or are drawn in our transistors. And if that is exceeding the voltage, at least what's coming here from our MCU, then the negative input is higher than the positive input, and that leads here our output to go down. And that means we get more or less a switched off bias voltage, and our resistors won't amplify any longer. So that is the game. And then subsequently, you know, the controller gets or recognizes that, oh, there is no current flow any longer, so something is wrong. And that means that then here our voltage drops again, so that our voltage which comes, you know, over our MCU, and the output comes up again. So that means, you see, that goes very, very fast, and that is what, you know, our bias voltage holds constant. So that is the game of switching and being in balance, so that the predefined setting gets observed here by our 2, you know, resistors, and gets always controlled and gets adjusted by this circuit. So, and you can imagine, if that is so important, if a circuit like this is so important, as I have described it here, then you may imagine that if something is wrong here, that really could have a huge impact of what we get finally as output power from our final stage. And that is something I have tested as well. So our both operational amplifiers are working fine without any problem, and our switch here, so that is a normal DC switch, if you like, is working as well. So we really can say that our APC circuit is working just fine. So that means, once again, I know that is a long story, but if you're really interested in learning radio electronics, that is really a very important thing to know. and therefore, yes, it is a lot of theory, but without understanding how it hangs together, you never will understand how a radio will work. So therefore, okay, we know now that our APC is fine, we have seen our voltages are fine, our diodes are fine, our pre-final or driver is fine, the pre-driver here is fine, everything is fine except from our final. And well, we cannot really test the final in circuit, so that is always a little bit difficult, but we know that everything in between is fine. So now we need to make a decision. Since there is nothing obvious, it seems that there is a problem here with our amplifier. And therefore, the next step is we simply swap out our amplifier and hope that we can solve the problem with it. Okay, so a little bit more theory. Why can we only hope that putting a new amplifier into the circuit helps? Yes, I will explain that to you in a minute. Here we have already prepared everything to swap out here our final stage, and of course I have here our new part, and you see it is a 2SK3476. So that is the new part which we gonna swap out. Okay, so look here, that is our final stage, the 2SK3476. And important to know here, let me enlarge it here a little bit, the power gain here. So that is what is described in our data sheet, our power gain. So that is the important part. Look here. So this is mentioned with 11.4 minimum. So you see it here that it is minimum. Normally you get a typical value and a maximum value. In our case, so the manufacturer only gives us a minimum, so we do not get more information about that. So what does that mean? I mean, okay, so it is tested on 520 megahertz and so forth, and with a voltage of 7.2 volt and so forth and so forth. Anyways, we only get 11.4 indicated as minimum gain and nothing else. Why is that all important? So remember, we tested here at our Q214 on C260 our plus 9.5 dBm. And remember, it was a little bit above 10. So that means we are here fulfilling our specs, so what Kenwood has given us. So that was that we said, okay, everything here in front is fine, plus 9.5. Okay, so let's take the 10 dBm, what we measured, okay? Okay, now let's go here down into our dBm table, and 10 dBm, okay, is 10 milliwatt, so that is not that important. But let's take our gain. So we have seen 11.4. Let's say, because our datasheet said 520 and we are here only on 145, so that means the gain might be a bit better because of the lower frequency. So let's assume it is 13. Okay, so let's say 10 plus 13, so that is then very, very simple, 23 dBm. So let's go to 23 dBm, which we have down there. Here is 23 dBm, and look, here we have suddenly the 200 milliwatt, which we have seen. Okay, so that is obviously in spec, if you like. Our service manual is telling us on the setting low, we should see half of a watt output power, which we are not able to achieve. Half of a watt. If we go up here, here is half of a watt. So that is what is expected. And we see that would be 27 dBm. And that means, on the other hand, if we are really getting here 10 dBm output in front of our final stage, okay, so that is what we have seen, and we take the guaranteed gain, then we somewhere come up here to 200 milliwatt. So that is exactly what we can see here, but we, according to the manual, to the Kenwood manual, we should see minimum 27, which is then our 500 milliwatt, right? And again, here is our scenario, so plus 9.5 dBm, our Q15, and the output is 0.5 of a watt, our expected output. And when we look here under the precautions, you see node 3 sets the transmission output to low. And that is exactly what we have done. And that is more or less according to our datasheet from our MOSFET. According to our datasheet, we are fully in spec. So that means, okay, we expect that this MOSFET transistor is able to have a better gain than specified in our datasheet. But on the other hand, if we go or we exactly calculate with what we have in our datasheet, we have to say it is in spec, right? So nothing is wrong if the radio only delivers 200 milliwatt, then it means that the amplifier is working just fine, no problem. But, well, is that really true? And of course, if they only gives us the minimum, no typical and new maximum dB gain, then, well, yeah, we can expect that typically it might be 17 or even 30, I don't know, but they don't do it. And they do it by reason, because they do not want a guarantee for more. And that means if you have something designed with this chip here, then, you know, even after some years, and I mean the radio is already 10 years or more old, yeah, you know, the transistor starts aging, and I believe it is a kind of aging what we see here. But the Toshiba, who is the manufacturer of this chip, can still say, hey, what is your problem? So we only give here our minimum gain and nothing else, because you can get a chip, a brand new chip, which only delivers 11.4 dB gain. And then that means what we have here in our circuit is fully in spec. And you see, that is sometimes a little bit tricky when you go to all this stuff and you see what's going on. So in this case we really swap the transistor with a brand new one, and we expect that the brand new transistor will us give a little bit more gain, so that we can come close, or we can exceed the values which are given by Kenwood. But as I said, no guarantee. And now let's go and let's swap out this little transistor. Okay, so we are going to prepare everything here for replacing our final stage. And well, it is not so easy as one could think. It is not only that we go with hot air and take it easily off, because when we flip it over here, then you already can see the issue we might have. So we have here a heat sink underneath, which is on one hand soldered here to our PCB, and on the other hand I believe that it is connected or soldered to our part. So therefore it will be a little bit tricky. So maybe you've seen my video where I were changing the finals or the pre-drivers for the ISO TH-D72. So there it is a little bit the same game, with the difference that these parts here are much smaller than what we had on the ISO 817. Okay, however, first what we need to do is to cover here our board, our parts, which, as you can see, very close here to the unit. So we need to cover that all in order to prevent that anything gets blown off. So that is now very important as next step. Okay, so as you see, we have covered here our PCB, and now we can start. Okay, so that was working fine. So as you have seen, it is off. And as discussed in advance, so we see here the breakthrough in our PCB, and you see here the ground plane from our MOSFET transistor. So yes, now next step is to flip the board over and to take our part off. Okay, so I've prepared everything, and so it should work quite easily, I hope. So let's see. Alright, here we have it. Very good. Okay, so I have already cleaned here a little bit our pads, and you see that we have all pads still there. So what you can see here as well is a little bit of our solder mask get off. We have a ground plane here and there, and that is kind of normal because we always need much heat to get these solder joints really to temperature. But it doesn't make any difference as long our pads are fine, and they are solid and stable. Everything is good. Okay, so next step is to put our new part in. Maybe that is interesting to you as well. So that is here our part. I just flipped it over, that you can see here the ground plane, right? So that is here what is connected to our little heat sink, and you see that are the both pins which were soldered here on this side of the board. So where we lost here a little bit of our PCB mask, and so you see how essential it is and how crucial it is to get the ground really soldered and connected, because otherwise it wouldn't work, and the heatsink, or the heat sinking at least, wouldn't really work. So that is a crucial part of what we are doing here. Okay, look, I have here now our component tester, and the part is already connected to the component tester. Of course, we want to know what's really going on with our part, which we have just taken out of our circuit. And so I've connected it, and now let's go over and let's watch the results. Okay, so everything is prepared, so let's start our test. Aha! Look here. So that looks quite promising. So one could think, okay, no problem, our transistor is just fine because our component tester is reporting an N-channel MOSFET, and it looks like that everything is fine. But now let's go over and let's do here writing the graph, and let's see if that still shows everything fine. Okay, let's start. Oops. Okay. So what do we see here? So while it is still driving, you see we really have a breakthrough. So the voltage is breaking through. So that is definitely not how a MOSFET, N-channel MOSFET transistor should look like. So that means even that if it is tested here just fine, you see that our graph is showing that we really have a breakthrough. And that is obviously the problem, or it was a problem. What we have seen that, yeah, it is working, because that is what our tester is saying. The MOSFET transistor is good. But when we go into the detail, then you see, wow, it is not fine. There is a serious problem with this MOSFET transistor. Well, and that brings me back to my video 263, where we made a modification on an older Heathkit curve tracer. And there you see, especially with MOSFETs and of course with other transistors, how it looks like when we have a breakthrough. And I very often already said that, you know, a MOSFET, or not a MOSFET, sorry, a curve tracer is really the last weapon we have if we have funny faults which a normal component tester reports as good. So maybe if you're interested in that background information, that might be the right video for you. But coming back here to the graph, we have written here. So here we have, of course, our VDS, drain source, of course. And here we have our ID. So that is the drain current, of course. And here you have the different gate source voltages. And you see that we really have a breakthrough. As example, so that is how it looks like, or it should look like. So we have here drain source voltage, we have here our drain current, and you see here the different gate source voltages, and you see what the graph looks like with the different gate source voltages. But what we don't see is that it is breaking through at, you know, a certain point here on our drain source. Drain source graph. So therefore you see the difference between what it should look like and how we have the reality here on our part. Okay, but I think that is enough on theory. So you see all the analysis we have done before very, very carefully, obviously led to the right conclusion: our MOSFET is dead. Okay, so let's start replacing the new part. Okay, so we have our new chip in, and okay, so you can see that we have quite nice solder joints here on our component side, but as we all know, the most challenging point was definitely here the heatsink, which we needed to get down, and that is, as you can see, done as well, pretty nice. So we have here at the ground the connection to the board, as you can see, and that means of course that we have the connection through the PCB to our part. Well, you've seen that we really needed to put a lot of heat into it, and that is always a critical thing, the critical issue, because there is a potential risk that you kill the component by too much heat. I mean, yes, there is definitely no other way, so you really need to get here the heatsink aligned as you've seen it, and that takes a little while. Well, and now we only can cross fingers and hope that everything went fine. And of course we have performed here a final check, so if everything is okay, that we have no component lost. So that often happens if you blow too much with the hot air station, so that can happen quite quickly. But well, we have really observed everything, and I did not find any problem, so we can now go and put it back into the housing. And don't forget the heatsink compound, so that is really important that you have really good connection between the two metals. Okay, so everything is prepared for testing. So we still have here our PTT line, so that is what I've explained earlier. So everything is back together so that we can test the unit. And radio is set to low power, where we had, what was it in the past with the old final stage, 200 milliwatt or so. Well, okay, let's test. So we have already prepared our power supply, and let me put in here our connector. Oh, okay, so we have received, not sure if you can hear it, here we have it, so we have received for sure, but that of course is not the important point. The important point is that we would like to have our transmit back, okay? So let me go over to the tester that we can see what happens. Okay, so our radio is still in receive, and when we switching it to transmit, we should see here our output power on low. So let me range that. Wow! Have a look! So it is back. We have 1.8 watt on transmit on low setting. So that means yes. Wow, I love it. So that is always the best moment, when you see that all what you have done is successful. Okay, so now let me put back here the top PCB, so that we can get better access to our buttons and switches, and then we can test a little bit more. Okay, so everything prepared here for testing. So you see it is already working. it is not back in its housing, but we can operate it here. So I've here directly connected to our output the power sensor for our Rohde and Schwarz level meter, and of course we will test it also here over our coax cable, whereby in our case, or in a case of a mobile, we only have this little antenna, so it is more important to see what is directly here at the port. And again, we go back in our test configuration as mentioned in our service manual. So we are on low setting and we expect to have 500 milliwatt. So let's go over to our tester. Okay, so let's try to do it this way. So let me press our PTT and let's see on low power what we get down on our communication service monitor. And yes, so we have 500 milliwatt, 0.5 of a watt, but it is important to see what we have over there. And you see now we have 0.54 of a watt, and that is exactly how it is specified in our service manual. So, and I go any further here. I mean, I've tested it completely. I can tell you that on the high setting it is lower than expected. So remember, that's a little bit the game with the data sheet of the MOSFET we have discussed a lot. So I believe when this mobile was manufactured, Kenwood tested all the MOSFETs which came in, and they sort them out to be able to have a higher gain. So therefore we do not achieve on a high what is specified. But anyways, you see that we improved here the problem, and you have seen that we had a broken transistor, our old MOSFET. We had that on the Korf tracer, and that was definitely a problem. Now we are back here on spec, and that is for 2 meters and 70 centimeters, and that was already a very long video, and I stop it here. And thanks for watching, and hope you learned something. Bye.